So we talked about our technical definition of what it meant to be differentiable for a two-variable function. It turns out that there's a theorem that's a really helpful theorem for being able to actually evaluate whether or not a function is differentiable. Rather than having to go through and find an error function and see that the error function satisfies the property of being locally linear to first degree. Instead, we can use this. And this theorem tells us that if my partial derivative with respect to x and my partial derivative with respect to y both exist and are continuous on some disk D, then we say that our function f is differentiable on that point D, where D is the open disk that's containing our point AB. Now this is a nice criteria because I can actually find partial derivatives and evaluate whether or not they're continuous or not. Those are techniques that we talked about from the previous section. So let's go ahead and take a look at an example. Let's say that I have a function f of xy that's given by the square root of 3x squared plus y squared. And I want to know, is this differentiable? Is this differentiable at the point 0, 0? Well, the first thing that I might check, is this function even defined at 0, 0? Because if it's not defined, if 0, 0 isn't part of this function's domain, then of course it's not going to be differentiable there. But as I plug in my point 0, 0, I see that, oh, indeed, when I plug in 0, 0, I get the square root of 0, and my functional value is 0. So it is defined, but in order to determine whether or not it's differentiable, we're going to take our partial derivatives and then evaluate them at the point that we're interested in. So first I'm going to take a partial derivative with respect to x. I'm going to need to use chain rule. So I'm taking the derivative of this whole chunk raised to the 1/2. I can use power rule. And I get 1/2 3x squared plus y squared all raised to the negative 1/2 times the derivative of the inside. Again, we're taking the partial with respect to x, so we treat y as constant. And the derivative of the inside function is going to be 6x. I can rewrite that if I wanted to. The 1/2 is going to cancel with the 6 to give me a 3x in the numerator. And in the denominator, I have the square root of 3x squared plus y squared. So now we have a function. This function is our partial derivative with respect to x. I need to know, does this exist, and is this continuous at the point 0, 0? So I can evaluate my function f of x at the point 0, 0, and I find out that I get 3 times 0 divided by the square root of 0 plus 0, which is 0 over 0, which is undefined. So we found out we didn't even get to try out our second step here. So we first saw that although our function is defined at 0, 0, our partial derivatives with respect to x is not defined at 0, 0. So I didn't get to check whether or not it was continuous because we know it wasn't even defined. So we know it's not continuous either. So our differentiability criteria fail. And we can conclude that our function is not differentiable at the point 0, 0. So let's look at an application of using these linearizations in terms of linear approximation. So, for example, let's say I have a two-variable function, and I want to be able to approximate points close to the point AB. So let's say this is my graph of my function f of xy. I have some point A in the x component. I have some point B in the y component. My functional output, is that even straight? Sorry, is the point AB f of AB. That's my point in three-dimensional space, right? And the idea is, let's say for the example that this function is a really messy function to work with. I don't want to work with this function. I would rather work with just a plane function, because a plane is really easy to compute values in. So instead of using this function, I might want to take the linear approximation of this function by taking that linearization, the plane that we found before. And then I can estimate values nearby the point AB using this approximation. So by points nearby, I'm going to introduce a new point by adding h in the x direction. So I have a new point, a new x coordinate of a plus h. And then k I'm going to add in the y direction. So I have a new y coordinate b plus k. That gives me a new point in the xy plane, a plus h, b plus k. And instead of evaluating this point in my original function, which for whatever reason might be a really messy function, it might be nice to be able to approximate its functional value by instead plugging it into our linear approximation function. So in general, we say that f of a plus h comma b plus k is equal to our function value at the actual point AB plus our change in x value times whatever our partial derivative with respect to x is. Times maybe, and here our change in x value is given by h, and I'll label this as change in x, plus our partial derivative with respect to y evaluated at our point AB times k, which is our change in y. So what is this saying? I'm doing a linear approximation because these are each linear terms, and it means that our functional output, this approximation output, maybe I should say our approximation output, is going to be as if I went straight up in the x direction given this x slope and straight up in the y direction given whatever my y slope is, and I'm going to be landing on a plane. And that plane may or may not actually align with this surface, my original function, but it's going to be a close approximation. So another way to think about this is in terms of, maybe is in terms of error approximations. So I could also conceptualize my change in f value. So here my original f value is given at f of AB, and my new f value is up here at f of a plus h comma b plus k. My change in f is going to be the difference between these two values, delta f. And the difference between these two values is f of AB minus f of a plus h comma b plus k. And I can approximate this change by saying that it's going to be about equal to my partial derivative with respect to x evaluated at AB times my change in x. Notice that's exactly what this term is, plus my partial derivative with respect to y evaluated at AB times the change in y. And this is exactly just an arithmetic, I can move these pieces around with algebra, but it's another way of conceptualizing what is my change in f, because this is sometimes referred to as my error approximation. Meaning that if I'm off a little bit in the x direction and a little bit in the y direction, how is that going to affect my n total as my z values? So let's go ahead and apply our error approximation idea to an example. So for this problem, we want to find the maximum error in the volume of a cone with radius 10 centimeters and height 25 centimeters, where my radius and height could be off by as much as 0.1 centimeter. I mean, this is something that you might actually want to know if you were a manufacturer of cones, and you would want to make sure that you have enough material to be able to make the production amount that you want to be able to make. You need to know what is the maximum amount that you could be off if we were sizing these cones bigger than exactly these dimensions. So in order to solve this problem, first we need to have an equation for our function of the volume of a cone given the radius and the height of the cone. And it turns out that this formula is 1/3 pi r squared times h. And I can remember this because pi r squared is the area of the base, h is the height, and it's 1/3 because a cylinder would be without the coefficient, but if you could fit 3 of these into a cylinder of that height. Anyway, that's how I think of it. So for our error approximation, we know that our delta V amount is going to be about equal to our partial derivative of V with respect to R evaluated at our approximation point. In this case, it's where R is equal to 10 and our height is equal to 25 times our change in R plus our partial derivative of V with respect to height, also evaluated at 10, 25 times our change in H. Our change in is also the error in, like what's the maximum error that each of these values can be. And we know that because that's given in the problem. We're told that the maximum area or error of each of these is given by 0.1. So I can replace delta R with 0.1, and I can replace delta H with 0.1 as well. So now we just have to compute partial derivatives, and the problem actually is relatively straightforward. So first I'm going to compute my partial of volume with respect to radius, and using shorthand that will give me 2/3 pi r h, treating h as a constant. And then when I evaluate that at the point 10, 25, I end up with 2/3 pi, I'm not going to write all this out, 10 times 25 is 250, that's where my 10 times 25, times 2 gives me 500 divided by 3 pi. Then I'm also going to have to take my partial with respect to h over here, and that partial is going to give me 1/3 pi r squared. The h term disappears. This is all treated as a constant in front of the linear term h. And when I evaluate that partial derivative at the point 10, 25, I end up with r squared, which is 100 over 3 pi. So now, putting all of these pieces together, I'm going to find out that my maximum error, my delta V term, at 10, 25, given the errors that we've talked about, is about equal to this term times 0.1. 0.1 is going to make it 1/10 as big, so I end up with 50 pi over 3, plus this term, which is exactly equal to this times 0.1. It'll make it as 1/10 as big, so I end up with 10 pi over 3. And adding these two things together, I end up with 60 pi divided by 3, or 20 pi. So what did this just tell me? This is the maximum error that I could have in my volume given a cone of these dimensions and a possible error in each of the R or H of 0.1. And hopefully my arithmetic is correct.